I think we can start.
Yeah, okay. So, hi everyone, it's a pleasure to introduce Enrique Vázquez, Professor Enrique Vázquez. He studied in UNAM, Mexico, and he got his PhD in 1991 with Professor Vázquez. And after that, he has been a full professor at UNAM in Morelia since 2007. And he has won 2 prizes, one in 2019, one Research Excellence Prize from the Mexican Physical Society, and then another one from UNAM in 2021. And finally, he has just finished writing his book, which is Astrophysical Flows and Interstellar Flows and Star Formation. So,
thank you.
Yeah.
Thank you, Andrea. Well, it's a real pleasure to be here. Thank you, Andrea, for the invitation and for the shelter in this week in between meetings. But it's wonderful to be here. This reminds me very much of my childhood because I actually learned to read and write in Italian. I lived in Milano for 1.5 years, but just when I was going in first grade of elementary school. So then I went back to Mexico ever since, and I totally forgot my Italian. So I would have loved to be able to give the talk in Italian, but it'll have to be in English. But anyway, yeah, my second last name is also sort of Italian, but it comes, I think, from Switzerland, the Italian part of Switzerland. So I have a lot of connections here, and it really touches my heart. So anyway, today I want to talk to you about 2 models that are more or less competing these days for the description of the dynamics in molecular clouds that are the sites of star formation in galaxies, and how do they compare? How do they try to explain the observed properties of molecular clouds, and how to perhaps try to distinguish between them? And of course, one of them is our favorite model, which is the Global Hierarchical Collapse model. And the Turbulent Support model has been around for essentially 5 decades with variations in time. But so it's very important to understand how these models interpret the properties of molecular clouds, and then why might one want to switch between them. So let's see if this is not working. Okay, so it's not working either. Perhaps now. Let's see. Yeah, okay, now it works. Does this work now? Yeah. So this is the list of my collaborators, a large number. Andrea was actually visiting our institute for 1.5 years, and we started discussing many things. And so the discussions have been very enlightening, I think, in both ways. Me learning about observations, and he trying to make sense of all our theoretical babble. But my main collaborators are Gilberto Gomez and Aina Palau, both at my institute. And so this is more or less the outline of what I will say today. First, some key properties of molecular clouds, just to bring them up front. Then a brief history of the theories about molecular clouds and their star formation activity, and how in particular we went from an initial view of collapsing molecular clouds then to a view that has lasted several decades, that molecular clouds should be supported against their self-gravity, and then perhaps back to the idea that they may be undergoing collapse at the cloud scale. And then I will, if time permits, discuss a little bit about how the models may be converging, because actually they've been around for several years already, and what issues remain to be agreed upon, and some tests that may help us decide. So some key properties of molecular clouds and the star formation activity. First, I would like to talk about what and where they are, what their internal structure is, the energy balance in the clouds, and then the fact that they are very inefficient at forming stars. So what are they and where are they? Well, actually, probably it's better to talk about molecular gas in general rather than molecular clouds. Because if you look at a picture, for example, of this picture of M51 with a Hubble image of the galaxy with superposed CO contours, actually you can see that the CO is extended essentially over the entire span of the spiral arms. So to say that there are clouds here is perhaps a little bit of an overstatement. It's just, to me, it's more like an ocean of molecular gas in the galaxies. This is, for example, how the data that from the Dame et al. Survey at the turn of the century, as analyzed by Marc-Antoine Vildechêne in France. This is a map of brightness temperature in a position velocity diagram. And these are the clouds extracted from Gaussian decomposition of the line profiles, which is a standard procedure among, in particular, radio astronomers with spectroscopic lines. And so this is a plot of where the centroids of the lines are in this position velocity diagram is. But really, the molecular gas is, like I said, it's like a huge ocean. You can see it here. No, I mean, you can see peaks in the distribution, but that doesn't mean that there's no gas around them. And of course, there's voids, but in some regions you really could. It all depends on where you set the boundary or the limit or your detection limit. So often we're limited in our definition of a molecular cloud or whatever type of cloud by the sensitivity, the noise, or whatever. In simulations, what we do, we don't have noise, but what we do is we define a threshold in density above which we normally take we define a cloud, but that's completely arbitrary, no? Okay, so where are they? Well, they are often found at the intersections of shells. And this is a map, for example, by Catherine Zucker et al. In 2022. And they have been finding, now that they can do tomography in the galaxy, they can really make three-dimensional maps of the gas and the stars. And they are finding that the molecular clouds in the solar neighborhood, the Gould belt clouds, for example, tend to be located at the intersections of supershells. And so, for example, they say that we find that nearly all of the star-forming complex in the solar vicinity lie on the surface of the local bubble, providing robust observational support for the theory of supernova-driven star formation. Yeah, maybe star formation can be driven by supernovae, but at the same time, we say that feedback sort of suppresses star formation. So the talk I gave a few months ago at some other meeting was precisely what should we make of the feedback? Does it promote star formation or does it suppress star formation? I think in general, it tends to suppress the star formation. So perhaps what we should think is that the main, as we saw in the previous map of the galaxy, of the M51, we saw that the gas lies essentially on top of the stellar spiral arms. And so this is a numerical simulation performed by Andy Burkert and Christian Ali, but they had not published it, so I invited them to publish it in our new paper, which is on their revision now. And this is a simulation in which gas is coming from the left. There is a straight rather than spiral potential well that is supposed to represent a spiral arm. In this case, it would be like a straight arm, not a spiral. And the gas comes in and then accumulates here. And then it forms a huge complex of dense gas in which supernovae are exploding, as you can see. But the supernovae are just rearranging this gas. they are not really forming new molecular gas. So that's the point of this simulation too, that we wanted to convey in the paper, and that's why I invited them to the paper. So perhaps the main factory of molecular gas in at least in grand design spiral galaxies is the stellar spiral potential. And then the supernovae just sort of rearrange it. Joao Alves calls this cloud sculpting, by the supernovae. So then another very important property of the molecular gas is that it is strongly Jeans unstable. For example, at a density, the base density at which we normally think of molecular gas, which is about 100 particles per cubic centimeter, and a temperature of 10 kelvins, the Jeans mass is about 45 solar masses. But a typical molecular cloud contains from 10 to the 3 to 10 to the 6, 10 to the 7, perhaps, solar masses. So they contain hundreds or thousands of Jeans masses. So this means that they have a very strong tendency to collapse. Of course, we know that there's turbulence in the clouds that tends to support them, but that's essentially the point I want to question here. Second, they have a lot of internal structure. And of course, these days we know that they have clumps, filaments, cores, and these are typically arranged in hub-filament systems or HFSs. For example, here is one such system in which there's a central hub, which is a dense condensation of sizes on the order of a few parsecs or about a parsec. And then it's apparently fed by filaments. And then on the filaments, there are secondary condensations that we tend to call cores. More or less, the nomenclature depends on whom you're talking with, but this is more or less the convention. So one very important question is, how does this structure come about? How is it driven? And so third, the energy budget and the scaling relations inside the clouds. As many of you probably know, there's the famous Larson's relations relating the line width of a certain line, a molecular line, with the size of the region where it comes from, and this line width size relation, or velocity dispersion size relation, in its present day accepted form, is that the velocity dispersion scales as the size of the cloud to the 1/2 power. And with this normalization, so it's on the order of 1 kilometer per second on scales of about a parsec. And this, by the way, means that the Mach number on these scales is on the order of 5. So it's already significantly supersonic. Then also there's a density size relation, and this is almost the original relation found by Larson in 1981, telling us that the volume density scales like the size to the -1 power. But this is also very important because it implies that the column density, which is essentially the density times the size or the length, is roughly constant for most clouds. Now, together, they imply what people sometimes refer to as the third Larson relation, which is that they seem to be in approximate energy equipartition. And I prefer to say equipartition than virial equilibrium because of what I'll say later. But so Larson himself plotted this graph where he plotted this quantity, which is essentially the inverse of the ratio of twice the kinetic energy to the gravitational energy. And this is what today we call the virial parameter. And as you can see, over 3 orders of magnitude in scale, there's a very, very weak variation of this quantity with scale size. So meaning that the clouds tend to be in energy equipartition between kinetic energy and gravitational energy. But this is most often interpreted as virial equilibrium. And so the idea is that the clouds are somehow in equilibrium, sort of like a globular cluster. But these are no n-body systems. These are strongly dissipative gaseous systems, which somehow would need some source of energy to keep driving this turbulence. Okay, so more recent data indicate that actually the virial parameter does have a dependence on mass, for example, so that for molecular clouds from the same survey by Marc-Antoine Miville-Deschênes, over several orders of magnitude in mass, you see this dependence of the virial parameter on the mass. So that the more massive objects tend to be more strongly gravitationally bound. This would be, for them, this would be the separation, the line dividing unbound from bound, assuming that the kinetic energy tends to provide support against the gravity. But that's a strong assumption, as I will mention. So, and this trend extends to massive clumps. So these are molecular clouds, GMCs, and these are massive clumps of sizes on the order of a parsec, masses on the order of 1,000 solar masses. And here you can see that the virial parameter scales with mass, but now the virial parameter is less than unity here. So these objects are below the equipartition line. This is the equipartition line again. Sorry, no, the equipartition line is here. And so these objects are essentially down here. So they're gravitationally bound. And you see also that the same applies to scaling between the virial parameter and the size. So larger objects tend to be more strongly gravitationally bound. This has been also analyzed by what we now, well, my group at least calls it the Mark-Hire diagram, the Mark-Hire's diagram. The Mark-Hire and his colleagues published this plot in 2009, where they plotted this other quantity, which we refer to as the Larson ratio. It's the velocity dispersion divided by size or the radius to the 1/2 power. So if you go back to Larson's relation, if you move the L to the 1/2 power here, then this should be constant. So plotting this thing, this should be constant according to Larson's line with size relation. But in reality, you see, and also they plot it against the column density. But interestingly, the second Larson relation would imply that the column density should be constant. And you see that the column density is not constant at all. Here it spans about 2 orders of magnitude. So this is the point where the previous survey by Solomon et al., 1987, would indicate that all molecular clouds should be. But actually, molecular clouds span a range. And so you have this correlation instead. That this Larson ratio scales like the square root of the column density. And what's interesting is that this is also a manifestation of energy equipartition. So this would be, if you move the R to this side, then essentially here you have kinetic energy and here you have gravitational energy. And so the two of them are more or less equal. So if you set this condition, then you get precisely this relation. So what this means is that this is essentially the same equipartition condition when you relax the constraint that the column density be constant. But so this relation is like sort of the generalization of Larson's line with size relation when you relax the condition of constant column density. And it has been argued that the constant column density is actually more like a selection effect. Yeah.
It's a stupid question. For the units on the x-axis, what that would correspond in centimeters to the -2. So 100 solar masses per square parsec is something like 10.
If I remember correctly, a solar mass per. I have a similar plot. It'll come up.
Okay.
I have a plot where I have moved the axes because I combined them. But I think, if I remember correctly, 1 gram per square centimeter is something like 5,000 solar masses per per square parsec, something like that. So if I remember correctly, I might be wrong. 1 gram per square centimeter is 5,000 solar masses per square parsec.
Discussed this with Kenny. I think it was the right.
Yeah, something like that. Yeah, sorry. And it's funny, when I see a plot in grams per square centimeter, I don't understand it, and I need to translate to solar masses per square parsec. But anyway, so that was that, okay? And so, like I said, it has been argued first, I think, by my former supervisor, John Scalo, that the constant column density Larson relation is actually just a selection effect derived from the fact of how we define the molecular clouds in the first place. Okay. Fourth is the inefficiency of star formation. So here a little bit of historical information is that supersonic line widths in the CO line were discovered by Wilson et al. 1970. And by the way, this is the same Wilson that discovered the cosmic microwave background. So they also discovered the supersonic CO line widths in molecular clouds. And one of the first interpretations of these supersonic line widths was that the clouds might be undergoing global cloud scale collapse. And this was proposed by Goldreich and Juan in 1974. But to me, 1974 was like a milestone year in the history of molecular cloud theories, because that same year, Zuckerman and Palmer in 1974 said, no, they cannot be globally collapsing. Why? Because one, the star formation rate would be too high. And they made a very simple argument or calculation. They said, the maximum star formation rate that you could expect would be the total molecular mass in gas mass in the galaxy divided by its mean free-fall time. And this gives you an estimate of about 300 solar masses per year, which is much larger by about 2 orders of magnitude compared to the observed star formation rate in the galaxy, which is about 3 solar masses per year. So their conclusion was, okay, they cannot be collapsing on the free-fall time. And also, they also gave the argument that they could not be collapsing because if they were, but they were imagining like a spherical cloud, no? Then you should see, for example, if you're seeing a cloud that is collapsing, you should see the absorption lines generated in the surface of the cloud to be redshifted with respect to the emission lines in the center of the cloud. So they would say that you should see these shifts between the lines from the absorption lines from the surface of the cloud and emission lines from the inner parts of the cloud, say, for example, from H2 regions and things like that. And because this was not observed at the time, they concluded no. So the clouds cannot be undergoing global collapse, and in general, they cannot be undergoing any radial scale motion. So they cannot be expanding, they cannot be contracting, they should be in equilibrium. And shortly afterwards, that same year, then Zuckerman and Evans suggested that the supersonic line widths instead correspond to supersonic turbulence, but microscopic. It had to be microscopic, meaning much on scales, turbulent motions on scales much smaller than the size of the clouds, in order to prevent this issue, in order to prevent the observation of shifting between the absorption lines in the surface and the emission lines from the center. Because that was not observed, they said, okay, the turbulence has, whatever support this is, it has to be on small scales. So in my mind, this amounts to just adding an extra temperature to the gas temperature. So in motions that are larger scale than the microscopic atomic motions or molecular motions in the gas, but much smaller than the size of the cloud, so that it produces an isotropic pressure and keeps the clouds from collapsing. Either that or magnetic support. And of course, we know that the magnetic support theories were the thing in the 80s and 90s. And but then the discovery that in general, the magnetic fields don't have enough energy to support the clouds sort of killed this theory, at least as a means of support. Magnetic fields may still have a role in delaying the collapse and making things a little bit smoother than they are. I don't have time to go into that today, but not in supporting the cloud. So I'm not going to discuss magnetic fields today. And so thus was born the notion of cloud support and equilibrium clouds. So now that I have more or less summarized the properties that we are interested in about molecular clouds, then I can go on over the two models. And by models here, this is important because the referee has been very insistent about this. The referee was telling us that actually many simulations these days do exhibit behavior that can be interpreted as being consistent with the global collapse theory. But here I'm not talking about the simulations. I'm talking about the conceptual models that we have in our heads and how they are formulated in analytical models in particular. And I'll go into the analytic models a little bit in a second. So not the simulations, but how we are interpreting them. And this is very important because, for example, if you take one message from this talk, is that the line width does not only represent turbulence. It can represent cloud scale motions, and we need to separate those two in order to really know how much the cloud is supported and how much it is undergoing contraction. So, okay, with that in mind, we can go over the premises of the turbulent support model. So trying to explain the two, all the properties that I discussed before. And like I said, no time to discuss the magnetic support here. So first of all, the fundamental notion is that the molecular clouds are prevented from global contraction by supersonic turbulence. It has to be supersonic because we need much more energy than we have in thermal energy. So the motions have to be strongly supersonic. Typically, we talk about Mach numbers of order 10 in the clouds. And this supersonic turbulence in general balances or perhaps somewhat exceeds gravity, so that this virial parameter, which we already defined, twice the kinetic energy divided by the gravitational energy, is in general larger of order 1. That is, and so we take one extra step and interpret this as meaning that the clouds are in virial equilibrium between turbulence and gravity. Or perhaps if this is larger than 1, then that they are supervirial. And so they might be expanding, or for example, in the model by Field et al. In 2011, they were suggesting that they could be pressure confined by the external medium. Then, because the clouds are in principle in equilibrium, they're not undergoing radial motions. In fact, that was the name of the model back in the 70s. It was called, I'm old enough to remember that. I didn't do science back then. I was like in high school. But when I learned it in graduate school, I learned it as the radial motions model, the model of the clouds pumping. So because there's supposed to be no radial motions, then the Larsen velocity dispersion size is a manifestation of the supersonic turbulence on small scales, for which, if it's strongly supersonic, then instead of the typical Kolmogorov spectrum for incompressible turbulence, you have the Berger spectrum, which has this form instead. So Kolmogorov spectrum has the kinetic energy going like the wave number to the -5/3. The Berger spectrum has k to the -2, where k is the wave number of the turbulence modes. And so if you write this in physical quantities, then the velocity dispersion should scale like size to the 1/2 power. So this is, and because there's no other motions, it was assumed that all of the velocity dispersion consists of turbulent motions that can provide support. Now, but this supersonic turbulence, precisely because it's supersonic and because the clouds are roughly isothermal, that's something I didn't mention, the clouds are roughly isothermal, and so supersonic turbulence is expected to produce density fluctuations whose amplitude is on the order of the Mach number squared times the mean density. So if you have turbulence with a typical Mach number of 10, then you expect density fluctuations that are a factor of 100 denser than the mean density. And so this was the proposed origin, and I was playing that game, as you can see here. This was the proposed origin of the density fluctuations, meaning clumps, filaments, cores in molecular clouds. And it was assumed that only the cores were able to collapse. So you had a turbulent fluctuation, and then what's interesting is that the cores are more or less at the size scale where the turbulent spectrum implies that the velocity dispersion becomes subsonic. That's typically on the order of 0.1 parsecs. And so that means that on the scale of the cores, the turbulence is not able to provide any further support. And then the clouds or the cores are free to undergo collapse if they are pushed above their gene's mass by the turbulent compression. So that was the idea of the supersonic origin of density fluctuations. And because the clouds are assumed to be in equilibrium, there are essentially no cloud scale motions, and therefore, this is what I already said, the velocity dispersion corresponds exclusively to turbulence. And also, because the clouds are more or less in equilibrium, they're not evolving. By definition, something which is in equilibrium is not evolving. So there was no specific theoretical prediction for the evolution of the clouds. And instead, the star formation rate is supposed to be controlled by the parameters of the turbulence, whatever it is. And so there has been a number of theories describing analytic theories. So these are analytic theories describing how the turbulent parameters, which are the sonic Mach number, the Alfvénic Mach number, the compressibility parameter, this tells us what fraction of the kinetic energy in turbulent motions is in compressible modes versus incompressible modes, and the virial parameter, which compares the kinetic energy to the gravitational energy. And there's all these theories. And for example, Federath and Klesen made a very nice summary of all the previous theories. But there are problems with the notion that turbulence can support the clouds. The first, and I think most important one, is that, like I've mentioned already several times, is that the turbulence was supposed to be on scales much smaller than the cloud itself, because it was supposed to prevent cloud scale motions. So it had to be microturbulence. But in reality, we know that the turbulence is not microscopic. For example, this paper by Chris Brunt and collaborators showed that the principal component of the velocity dispersion in clouds is given by what they called a dipole contribution, meaning that you have one part of the cloud going in one direction, the other part of the cloud going in a different direction. And so the principal component of the velocity dispersion is at the scale of the clouds themselves, not microscopic compared to the clouds. So the turbulence just doesn't do what it was supposed to do in the first place. Second is, it would be some sort of a miracle if turbulence knew how to adjust itself to virialize every scale. And in fact, if it did, it would not satisfy the Berger spectrum or the Larson relation. Because, for example, Heyer and collaborators showed that actually the Larson ratio, which should be constant for just supersonic turbulence, actually does scale with column density to the 1/2 power. So meaning either you satisfy the Berger's turbulence criterion, or you satisfy the Heyer criterion, but you cannot satisfy both of them at the same time. So somehow it doesn't work. It only works if you keep the column density constant. But that means if you just focus on one range of column densities of the objects. Then finally, if turbulent energy decreases with scale, then why do cores, even the subsonic ones, continue to fragment with similar patterns as clouds? So for example, this is a very interesting example in which Jaime Pineda and collaborators in 2010 first observed this famous quiescent core B5, and they observed it with a single dish telescope. And then they described it as a prototypical example of the of the coherent core, in which the velocity dispersion goes subsonic inside, and so it was sort of in equilibrium. Yet, this following year, they observed it with an interferometer, and they found all sorts of substructure in it, and the same type of substructure that you see in molecular clouds. So hub-filament systems, and so this is a condensation and filaments, and so, but this cannot be formed by turbulence, which was the premise of the molecular of the turbulent support or proposed origin for the structures. So in fact, I was puzzled by these things, and so in in 2007, I started looking for the origin of for the origin of molecular cloud turbulence, and so I did some simulations of converging flow, so compressions in the diffuse atomic gas that would form a cloud. There had been papers before showing that, in particular, Ethan Vizhnek's instability, nonlinear thin shell instability, that shows that converging flows generate turbulence by the nonlinear thin shell instability combined with the Kelvin-Helmholtz instability in the condensed layer, compressed layer, and that generates turbulence. So I was thinking, oh yeah, so that should be the source of turbulence in the molecular clouds. So, and I was hoping to see in this simulation that the turbulence generated by the assembly of the clouds themselves would keep them from collapsing. But to our surprise, it did not keep it from collapsing. You can see it here, that the cloud forms, so the streams are coming in from the left and right, and boom, bang, the cloud collapsed. In fact, it was very interesting because the collapse proceeded in a pseudo-virial way, meaning that this is the thermal energy of the cloud, this is the kinetic energy, this is the gravitational energy. And of course, because the cloud was being assembled, it started with essentially no gravitational energy, and then it was growing. And then this is the kinetic energy generated by the instabilities in the shell. And you can see that it is moderately supersonic. It was not strongly supersonic, it was moderately supersonic. But then, once the cloud becomes supergenes, which happens here, then it begins to collapse, and then it drags the kinetic energy along with it. And then it looks like it's in virial balance because the kinetic energy is about half the gravitational energy, but it's not in any sort of equilibrium, it's collapsing. And that is because under collapse, you also have the condition that the kinetic energy equals the gravitational energy. So, and by that time, then the cloud became strongly supersonic with Mach numbers of about 10. So that's what led us to thinking, okay, so maybe the velocity dispersions that we're seeing in the clouds are actually a reflection of collapse after all. So going back to Goldreich and Quantz. And so now to finish, I would like to, so I think that's about as far as I'll be able to go. I would like to give you the premises of our model, but it hasn't only worked by us. Actually, what I consider the Bible of the cloud formation and cloud evolution paper is this paper by Hartmann et al. 2001, where they collected all the necessary criteria, how the clouds grow, how they become gravitationally unstable, how they become molecular. So I highly recommend it, although I had to read it like 3 times to understand it. But anyway, and then Mordecai McLough and his group has also been working on this. So the main premise is that the clouds do not contain strongly supersonic turbulence. They only contain moderately supersonic turbulence, Mach numbers of order of few. That are good to give you nonlinear density fluctuations, but not to induce the collapse directly from the turbulent compression. Then what happens? You assemble the cloud, and one very important thing is that when you assemble a cloud from the W and M, so in the atomic medium still, and the warm neutral medium, and you induce a phase transition to the cold neutral medium, the temperature drops by a factor of 100, the density increases by the same factor because that keeps the pressure constant. Because of thermal instability, it's the isobaric mode of thermal instability, but that implies a drop of a factor of 10 to the 4 in the G's mass. So all of a sudden, when you convert a chunk of W and M, warm neutral medium, into C and M, you have made it 10 to the 4 times more gravitationally unstable than it was before. So we're arguing that the collapse starts at the largest, so that tells us that you form a piece of a cloud, and that is born gravitationally unstable. And then as the collapse proceeds, so the second point is that the collapse goes from the outside in. What begins to collapse first is the outer parts of the cloud. And then, as is well known for an isothermal flow, as you contract, the density increases at constant temperature, then the Jeans mass drops. And so that keeps reducing the Jeans mass. And that makes subsequent smaller mass density fluctuations sequentially gravitationally unstable. So it's like you start collapsing from the large scale, and then things on the smaller scales begin to collapse once the Jeans mass reaches their mass, and so on and so forth. So we call this like a collapses within collapses scenario. It's hierarchical. And it develops, so the small scale collapses are sort of riding along the large scale collapse. This means that molecular clouds are not in equilibrium and contain infalling motions at all scales with them. And that means that there's accretion at all scales. So we're considering that if we form a cloud, like I showed you in the animation, in fact, the cloud itself is accreting. And the molecular clouds then, because they have cooled and become denser so rapidly, then they contain a large number of Jeans masses. And that means that the collapse is nearly pressureless. And this amplifies the anisotropies. And I will get back to this in a second. And because the cloud is collapsing, now it is evolving. And it's changing. So it's, if you define a cloud, like I said at the beginning, by, for example, a density threshold in our simulations, then you see it accreting mass. So its mass is increasing. Its density fluctuations are increasing, and so is its star formation rate, until you are able to form sufficiently massive stars that they destroy the cloud. And this means that what's very interesting is that in our simulations, we typically find that the cloud is destroyed when about 10% of its mass. Well, this is for a typical, a mean size, an intermediate size intermediate mass cloud of about 10 to the 4 solar masses. And then just ionizing radiation from massive stars is enough to destroy it. And typically, we find that the clouds are destroyed when about 10% of their mass is it has been converted to stars. The rest is dispersed and it's returned back to the ISM, and that prevents us from facing this conundrum of excessive star formation rate. So the star formation rate is controlled by the evolution of the collapse, and because they contain infall motions, the velocity dispersion, and therefore the virial parameter, contain a contribution from the cloud scale motions, and that has to be taken into account. So you cannot assume that the virial parameter is directly a measure of cloud support. Somehow, and I've been insisting that to my observer colleagues, we need to distinguish what fraction of the kinetic energy is in infalling motions versus what fraction of the kinetic energy is in truly turbulent motions that contribute to supporting the cloud. So I have a justification for this, but I don't, maybe I just have like 3 minutes. So maybe I just want to go on the main ones. Collapse is from the outside in, and that was very interestingly already in Larson's 1969 simulations. For example, this is the plot from Larson's paper, and this is the collapse in his spherical collapse simulations. And here you have, this is the well-known shape of a collapsing sphere, which has a central flat part and an r to the -2 envelope. But this central flat part is actually smaller than the local Jeans length, the Jeans length for this density. So this central part is itself Jeans stable. It's only reducing its size because it's been crushed by the collapse of the outer parts. These are coming in. And the collapse is actually, so this is a plot from a paper by my former student, Raúl Naranjo Romero. where he actually simulated numerically the collapse. And this is a plot of the velocity at different times. And so this is the infall speed, for example. And so the gas, so if this is the center of the core, the gas is coming in this direction. And you see that the velocity is increasing and the peak of the velocity is approaching the center. So at the time when the peak of the velocity reaches the center, at that point, you form the singularity in the mathematical solution. For us astronomers, you form the protostar and you cause a strong shock at the center, but there's no shock before then. And the peak of the velocity is just coming at you. So I like to think that the collapse is sort of like a tsunami coming from the outside, and then the gas is falling if you're at the center of the core. So the collapse is from the outside in. This is contrary to Schu's solution of inside-out collapse, but that's because he assumed a particular initial condition, which was the singular isothermal sphere, which had a singularity already at the initial condition. So he completely bypassed the pre-stellar stage of the collapse. So that's quite important. The other part I would like to just mention is that Lin et al. Showed so this is really going back to the masters in the mid 20th century. Lin et al., so it was Lin, Mestel, and Schu, showed in 1965 that pressureless collapse amplifies anisotropy. So, and this is because the collapse goes faster along the shorter dimension of a triaxial ellipsoid. So if this is an ellipsoid, which I didn't manage to make it look like an ellipsoid, but assume this is an ellipsoid and it's somewhat shorter along this dimension. So it collapses first along this dimension to form like an oblate spheroid. Then assume that this direction is shorter, and then it collapses along this direction to form a cigar-shaped thing. So, and this is very similar, for example, to what we see in numerical simulations of actual filament formation from collapse. Here's the animation. And so you can see this is again one of those simulations where you have the collision of streams. You form a turbulent gas, a turbulent cloud in the middle, but it's not very strongly turbulent. So what you see is, let me show it again. Yeah, the cloud is turbulent, but you see a very slow, large-scale collapse that is assembling the filament. And this filament, and then because of the fluctuations, and these are true turbulent fluctuations, you get irregularities, and the faster and the denser part takes over, runs away from the others. It creates a hub, and then the rest of the gas flows along the filament. And I think I should stop here, and I would just like to finish. So you see, I had enough for another talk. But this is my table comparing the two models. And of course, now I think the task is to, because the two models are essentially designed to explain the same set of properties of molecular clouds, then we need predictions from the models now to be able to distinguish between them. And so there are a few. For example, the fact that gravitational collapse doesn't give you strong shocks until the very moment of singularity formation. So while instead the turbulent model predicts that all structures are formed by supersonic compressions. And so in the turbulent model, you should see evidence of shocks in the neighborhood of clumps, filaments, and cores. While in the JAC model, you don't necessarily have to see that. You can if there's additional turbulence, but it's not required by the mechanism, and other things like that. And so that's discussed in our paper. And the other thing I wanted to say is that this is the book that Andrea mentioned. And for example, I try to review the theory, but going beyond the standard theory. For example, I do discuss the outside-in collapse, the anisotropic collapse. For turbulence, I discuss both the incompressible and compressible theories. For thermodynamics, I discussed both the linear and nonlinear thermal instability, the fact that the nonlinear case gives you phase transition fronts. So there's nothing like cloud confinement by a warm phase. You can have flow perfectly moving across the phase transition fronts. And that's it. And the virial theorem, I discussed both in and out of equilibrium in the presence of accretion and in the presence of turbulence, driving and dissipation. So it was 10 years working on this, and I hope that it can provide a useful summary for the community. And so with this, thank you.
So are there any questions?